if you don't know who Bob Kuykendall is, you probably were born yesterday. Bob is the only sailplane kit manufacturer in the United States, North America, and probably South America too.
Maybe the world.
Maybe the world. There are a few kits I think are still available from Europe. And Bob is going to let us know about something new.
Hi everybody, can you hear me? Is this working? Yeah. All right, so today, typically when I came to ESA Tehachapi, I'd bring all parts, no charts, and just talk about stuff we've done in the shop, stuff we've built, stuff we've broken, stuff we've tested, stuff we've flown. Today I'm going to tell you about stuff we're working on, but I don't have any of the hardware here whatsoever. It's all in the airplane, and logistics prevented me from bringing the glider down here. So here's me, all charts, no parts this time. And what I'm talking about is a thing I call the CMS-25 version 1 camber management system. And when it comes down to it, camber is basically just flaps, but I prefer to think of it as managing camber because camber manages CL. And CL is what you want to optimize. You want to optimize your airplane for localized flying conditions. So, CMS-25, and 25 comes from the Streeter metric. When I bought out Streeter's old stuff, we knew that he'd done HPs through 22, and when I looked in his old design notebooks, I found a table of bending moments for a 50-foot wing spar labeled HP23. So when I started making gliders based on the Streeter legacy, I started with 24, and now we're up to 25. So CMS-25 version 1 is a proof of concept automatic flap system. Let's see if I can. And so I'm going to do who, what, when, where, not necessarily in the order, but we're going to concentrate on the W's. And who, I'm the HP24 guy. This isn't me, by the way. This is Brad Hill, my old design development partner. This is his Tetra 15, which is pulled from the HP24 molds. It's a lightweight version. It's currently operating out of a Freda. A guy named Florian is flying it. It now has over 1,200 hours of flight time, and so far as I know, they've had no trouble with it. And that's Brad Hill, and that's my glider. This is the kit thingy that I try to sell. Current kit price, $42,000. And you get everything you need to just glue together, drill holes, install bolts, glue a couple of things together, do a bunch of finish work. If you've ever painted a car, the finish work goes pretty fast. Yeah, there's all my parts. And I got a whole bunch of slides, so I'm going to rip through them really quick so I can clear some time for questions at the end. This is what I'm flying right now. This is serial number 3. I borrowed back from a client. This year I put 30 hours on it. Last year was about 40 hours. And I'm piling a bunch of flight time on it. Just, well, number one, because I like flying gliders, and I like flying the glider that I built. And I'm having a hell of a good time flying it out of Siskiyou County Airport up by Montague. That's how it looked just before I took off. And my concentration has been on operationality. I want more than just a kit glider you build. I want a glider that once you finish building it, it is worthwhile having and operates exactly like your typical European sailplane. Keep moving. Who? This is my friend Paul Armstrong. I've tried to do auto flaps in the past, but I had trouble keeping a team together. I'm not an engineer. I'm not the smart guy behind this stuff. I'm the make it guy, I'm the do it guy, I'm the try it out guy. And so I put together a team to actually build a camber management system. This is Paul Armstrong. He's an expert in embedded systems. He did all of the circuit design for this, and it's a pretty complicated set of circuits, 3 or 5 circuit boards using the ESP32 chipset. We'll get a little bit more into that moving forward. But he did all the electronic design, all the circuit board design, all the coding, and he's pretty much my hero on this. Here's the other guy, Dr. Stephen C. Smith. If you've watched Mythbusters, you know him as Dr. Smith. He's been my friend since the early 1980s. I helped him build that RV-8 that he's sitting in right there, and he did the aerodynamic aspect of automatic flaps. Basically, his contribution was to analyze the handbook of the glider that my glider is inspired by, and from that reverse engineer a polynomial that matched coefficient of lift to flap settings. And what our box does is infer coefficient of lift from some data, but we'll talk about that a little more later. Okay, we're getting into why. And I've heard all of these many times over, and my job here is to refute them. So why not automatic flaps? Why not an electronic camber management system? People say, oh, it's too heavy, you have to add too much stuff to the glider, right? It doesn't offer a compelling performance advantage, you know? It's just moving the flap handle. How hard can that be for a pilot? And and this is the most ridiculous one, it separates the aviator from aviating. And I hear the same argument from people who drive Miatas, because they say, oh, you've got to get the stick shift version, because, you know, rolling the gears is an essential part of the driving experience, and yada yada. I have a Miata. It's a great car. It's got automatic transmission. All right, moving forward. So these are the essential arguments against, and here's my rebuttal. The system I've built adds about 5 pounds to the aircraft. Most of that is in the actuator, which weighs 2.5 pounds. There's a couple of pounds of, well, not even a couple, maybe a pound of wire, and maybe a pound of other, you know, the controller and the cockpit handle and other stuff that I'll show you. But if your glider has a reasonable sized battery, and my glider has a 23 amp hour lithium battery, everybody ought to be using lithium batteries by now. The 18650 based commercial cells are plenty safe enough. So that's not a compelling argument. It automates a determinate task. And by that I mean, if you know the CL you're operating at, you know what flap setting you need to be using, and it adds nothing to the flying experience to simply move a handle to accommodate that CL setting with a camber setting. And by doing that, by automating that determinate task, you free up attention for tactics and strategy. One of the essential things I learned from racing motorcycles at the GP level is that there is no such thing as multitasking. Every little thing, even things with muscle memory, require attention, and you only have so much attention to spend at any one time. And if you can free up some attention by letting the computer move the flap handle, you can do smarter things tactically and strategically. So here's flaps from the airplane handbook perspective. If you look in the handbook for one like the one that inspired my glider, it says at this speed, you know, at some standard assumed weight level, at this speed, you'll use 15 degrees of flaps, or 10 degrees of flaps at that speed, or 5, or 0, or -5 above some other speed. And if you look at this curve, this black line represents the ideal flap position, the ideal camber setting for that specific CL requirement. And if you look at the handbook setting, if you see the stair step, between those two is an area. And I'm not an expert, I barely got through integral calculus, but I do know that there's an area there. It is non-zero. But it's not even that good. Your typical pilot probably doesn't operate to the handbook setting all the time, right? I know lots of pilots who have two flap settings. They never bother with +15 because they use powerful tow planes and they get off the runway pretty quick. So they never use 15 And they never use 10. They have 2 flap settings. In a thermal, they thermal at +5 because that feels right for their glider. And as soon as they top out a thermal, they immediately push over to -5. And at -5, they start accelerating away from the thermal to get to the next one. And all that time they're accelerating away from that thermal, they're accumulating a huge error volume between the flap setting they're using and the flap setting that they ought to use. And as I said, I'm no expert in integral calculus, but there's a big difference between that area and that area, which CMS gives you. In my system, the automatic, the camber management system I'm designing, has flap setting intervals on 1 degree centers. So if anytime it detects that you're more than 1 degree from the optimum setting, it immediately moves it to the optimum setting. And the error, you can barely see the blue error area until you get up into some pretty high speeds. So, and I was saying I'm no expert in integral calculus, but I'll bet that blue area is a lot smaller than that one. All right, so there's my performance argument. People have said, oh, you know, you can just move the handle. If you move it right, you're gonna be close enough. And that's true, but I can definitely guarantee you some performance improvement. So, and I'm moving pretty quick through this so I can get to questions. The curves I just showed you is kind of notional. This is the actual curve we're working with. This is the curve that my friend Dr. Stephen Smith provided for us. And it's, oh my God, it's a polynomial that starts with to the 5th power 4th third squared x and then a constant. And he reverse engineered that from these stair steps that he found in the operating handbook. And this is for, as I was saying, the glider that inspired mine. It has the same airfoil and the same characteristics. So, and I think he's actually adjusted that slightly to accommodate what he knows about my glider. So that's the polynomial that's built into the box we're looking at. And that's kind of why. And oh, by the way, that handbook I was talking about, it gives you flap settings for speeds, and it doesn't talk about G-loading. And G-loading affects lift, and lift is essential to, CL is essential to lift, and what you're trying to do is set flaps to CL, not to the speed. And so that's one thing our system does. It does have an accelerometer built into it so that it can infer CL from the prevailing conditions. These are the parts that I would have brought if I hadn't already built them into a glider. And it's better if I just show you the diagram. The diagram is a lot more effective. This is my system. You can see that it has a display that lives on the instrument panel that tells you what the system is doing. And it's also got a couple of buttons that you can use to configure a couple of parameters in the system.
Whoever has this black card, could they move it, please? They want to take their glider out.
Oh.
This one? Yeah.
All right, moving on. My system has a rather robust cockpit lever. I hate putting little switches and little dials and little knobs into cockpits for essential primary and secondary flight controls. If you kick that knob off, you might be in big trouble. So I designed a big, rugged, aluminum flat handle into which we built a bunch of electronics in a absolute encoder that tells you the lever position. And you can see that it has about 8 manual flap settings that you can choose manually. And it's got an automatic setting which flips it into the automatic mode where it uses its sensors to infer CL and set flaps accordingly. Our controller, as I was saying, has an accelerometer into it. It has a CAN bus that it uses to talk with the lever and the display. And it has power wires that it uses to drive the actuator to actually set the flaps. And gets position feedback from the potentiometer built into the actuator, so it always knows where the flaps are. It also has pneumatic connections and pneumatic sensors for pitot and static, so it knows how fast you are and how high you are. So that's basically everything there. And that's kind of what I showed you there, all cast out on the floor. My controller is that little box there. It is a bespoke custom controller based on custom circuit boards using the ESP32 chipset. But as I was describing, well, let's move forward. Here's what my controller is and does. ESP32 based microcontroller. It delivers power to the actuator. It can measure how much power it's delivering to the actuator, so it can detect how much strain the actuator is under. It can create kind of a curve of actuator demand, so it knows, whether it's getting hot or not, and it can detect whether the actuator is stalled, so it knows not to try to deliver too much power to it. It has feedback sensors that it uses to sense the position potentiometer inside the actuator, so it knows where the flaps are. It has those pitot and static sensors for airspeed and altitude. And it has a CAN bus controller that uses talk to the display and flap lever clusters. It also has a USB port that we use to program it. So back when I show you that picture of Paul, let's see if I can get back to that. Boop, 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 boop. Paul, there's Paul working at his laptop computer plugged into the USB port on the controller, tweaking it while it's installed in the airplane so that, we're doing a little debugging, so we're getting ready to fly. Let's see if I can get back to where I was. Boom, boom, boom. Yeah, there we are. There. So that's the controller. That's what? There's my cockpit controller again. And again, I was saying I like nice rugged controls, so I designed a nice little cluster that you couldn't damage just by kicking it when you climbed in or out. There's the display that lives on the instrument panel. M is for manual, and it'll say A when it's an automatic. Manual, 10 degrees, current flap setting. Battery's running low, system health is good, and if I were you, I'd be using plus 15 instead of 10 based on the current airspeed of 8 knots, which is well below stall speed, but for that you want as much flap as you can get. And it's in this nice little carbon fiber enclosure that I made because it lives on the instrument panel because I don't have room for another instrument in the instrument panel right now. Here's the actuator we're using. It is a standard for Galley automation actuator, and at Steve's insistence, it will drive the flaps from full range, from full negative, -5, to full positive, plus 15 in 2 seconds. And Steve says that's important when we get into flying and tuning this thing. If we do it right, we can extract energy from gusts, which is one of the performance gains we're looking for. But it'll take some tuning to figure out if we're actually doing that and how to optimize that. That's our actuator. Here's a little story about our mechanical integration. Here I've got my fuselage in the shop and torn open, and we're installing all this junk. And part of the magic, one of the reasons that I'm doing this, and I'm doing it now, is basically because I can. I've got a kick glider where I can take out a dozen screws, remove a huge bunch of airplane, and reach deep into the belly of the beast to install the actuator. And in few other sailplanes, especially European sailplanes, is this a practical endeavor. For a lot of these things, if you want to reach into the guts of your glider, you get the whole side off. And when you're done, you get the fiberglass and the resin out, and you patch that hole. And if you didn't do that, you'd never see that stuff, you'd never reach it. But I've designed a glider for construction, home workshop environment, and one of the side effects of that is that I need to make access so people can install major control system parts in their home workshop environment. So this is where, this isn't a really great slide, it's kind of an eye test, but here in the belly of the beast, I'm installing the actuator, and it drives this torque tube, which I call the flap torque tube, which raises and lowers this torque tube, which I call it's a lateral torque tube, which has push-pull tubes that drive the aileron, the flapper-on auto-connect funnels that are at the inboard ends in between. So, you know, there in the belly of the beast, it'd be really hard to get to somewhere else. We'll have a more generic solution for that later, but for this prototype, this is the most effective and fastest way to do that. And here's a picture of us reaching down into the belly of the beast. There's one of the torque tubes I was talking about. Here's my auto-connect funnels, 12 screws, and we're in there and we're doing it, no sawzall required. So, where are we today? I'm about to fly this thing. We've got everything put in, we've got the software debugged to a reasonable flightworthy level. It doesn't do exactly everything we intended to do, but it does the basic stuff really well. And we've showed that the error cases are self-recovering. So everything's installed, the software is debugged, and it's ready for first flight. And the next time I go to where the glider is, if there's anything like flying conditions, I'm going to fly it and make sure it works. And that's our plan. Let me back up a little. That's our plan basically, is we're going to fly it, see if it works, see how well it works, see what it takes to make it work properly. And what we've learned so far is a potentiometer feedback built into commercial linear actuators actually kind of suck. The difference between most flap settings, most 1 degree flap settings, is only a few millivolts. And we have to do, my friend Paul Armstrong has to do some pretty neat software tricks to reliably detect these changes in the feedback and to predict, you know, what the error band is and how to get exactly where he needs to and what he needs to do to prevent it from having to jitter between different flap settings. We also know that absolute rotary encoders kind of suck. I'm using one of those in my lever, flat position lever, and the way it works out is that we're using one that offers 128 different gray codes per rotation, and because our handle only goes 90 degrees, for the 90-degree traveler, the handle, there's only 32 of those codes. And so between some of the positions, there's only a couple of clicks, and sometimes you don't quite get those clicks. So moving forward, we're probably going to use, hold for a second while that's all our noise. How are we doing out there?
It won't take long, it'll be gone.
All right, I'm just gonna stand down for a minute.
That's 11%.
Oh, it is electric. Is it? No, that's not electric. Yep. I'll even be quiet if it's electric.
It's the rotary.
Ah.
That's Jim Stanford.
Well, can you hear me well enough? Shall I just continue? I'll just talk real loud. How's that?
Yeah, that's better, not better.
All right. So going forward, instead of the potentiometer, we're going to use a rotary Hall effect sensor that Paul Armstrong says gives us about 4,000 a circle revolution, a 360-degree resolution of about 4,028 notches, or whatever the digital equivalent is. And for the cockpit handle, we're probably going to either rotate our. Yeah. Is that Dave Ryan? Who is that?
No, it's Jim Stanford.
Ah. Oh.
Juliet Sierra. Same aircraft.
I'm betting he can't run that thing for too long on the ground without overheating, so I don't think this is going to take too much longer. There's his turn. And
There he goes.
He's got the wings level, so he's not going to I wish I had the $250,000. All right, so for the cockpit controller, we're going to either use a different encoder, or I'm going to use a toggle switch and increment and decrement between the different manual flap settings, and have a button that you press to toggle over into automatic. And we did that with a previous attempt at this system, where anytime you move that manual toggle, it toggles in manual. And then if you want to go automatic, you press the side button for automatic. We might do that instead of our cute little handle that's caused us so much trouble. Okay, so what's next? This is it. I'm going to fly it, get some hours on it. Next, we're going to start adding features, because our end goal here is to produce a commercial system. I mean, I like doing this stuff for fun. I do it for fun, but I'd eventually like to get paid a little bit for this development effort. So our end goal is to make a commercially available retrofit system that people can put into manufactured gliders. So we're going to have a config app on your phone that you can use to set parameters, set empty weight, adjust the polar, the polynomial, stuff like that. So you can customize that polar that matches CL to speed, or CL to flap setting. Here's a neat one I'd like to try. I mean, we all know how effective artificial intelligence is, and most of us know that it's kind of shit. But I've been in the machine learning business for about the last dozen years, and I know that machine learning is a valid engineering pursuit, and this might be a good place to do something. If you know what was happening for the last 10 minutes, and if you know that last 10 minutes wasn't usual, you can make a pretty good guess that the next 10 minutes is going to be sort of like that one. So I'm pretty sure that if we do some logging and some machine learning, we can, in real time, adjust the system parameters to give another minor performance increment. And I know in the open class, these guys have killed for a 0.5% performance improvement. So this might be worthwhile. And as I was saying, end goal, productize the design. Come up with a smaller and easier to implement cockpit control. Integrate that display unit with the cockpit control, so you got one less thing to put into the cockpit. And simplify the overall system integration, so that we can fit this into a JS3, let's say, or the latest Ventus, or not the latest Discus, but you know, the latest and greatest European sailplanes, so we can actually sell these things, get some money, and maybe someday we will have that $250,000. Not anytime soon, but we can always hope. Oh, back up. Oh darn, sorry. Let me find my cursor. It's in there somewhere. Feeding view. All right, so if I go back, no, sorry. All the way through, the long way. Where are we? We learned what's next. Oh, that's it. That's all, Q&A. So, first question.
Can you still retain your manual flap?
Can you still retain your manual flap? That's a very good question.
In case you run out of batteries.
In case you run out of batteries. The answer is no. Not in the system I've designed. I thought carefully about incorporating manual reversion systems that would let you manually change back. And in the case of the glider I'm working with now, I'd like to do that, but it adds so much complexity that I'm worried that the added complexity would actually reduce system reliability more than it improves it. That manual reversion might hang up or catch, or I don't know what. I have landed this glider in every flap setting it has, including -5. So personally, I'm not too concerned about this. Going forward on a productized version of the system, we will seriously consider that, but it's not high on my priority stack. If people can't land their glider in negative flaps under, you know, on occasion as a semi-emergency, then they probably shouldn't be flying cross country. Next question. Oh, well, start there.
So do you have any sort of interrupt function in the event of like a runaway if you have your controller fails?
Do we have an interrupt system?
Kind of like a trim runaway situation?
Well, that's a good question. You know, we know from the Boeing 737 the trim runaways are can be serious affairs. But in this case, all I have is and I installed it specifically for the purpose of the system. I installed a mechanical stop in the belly of the beast that I was just showing you that mechanically prevents the system from going any further than -5 or +15. Excuse me, -7 or +15. So in the case of a runaway, it will meet that mechanical stop, and even at full power, will stall the motor and it will stop there. So it's not going to go to something crazy like -20 or +45. But other than that, we don't have anything built in. Yeah,
Andrew,
stand by, please. Okay.
if you go straight from manufacturer linear actuators, some of them will have backdrivable dual encoded dual motor versions, so that you can have at least electrical redundancy.
Say it again, please.
Sometimes if you go directly to the manufacturer for linear actuators, you can find that they'll have dual encoder and dual backdrivable motor versions. And build some redundancy into the system that way.
So if we go to the manufacturer, we can basically get dual redundancy for a lot of the feedback and drive features.
Just in that one unit.
That's interesting. I'll consider that. For this prototype, we're just using off-the-shelf stuff because I want to get in the air and I want to fly it. But that'd be important to consider. I mean, sticker shock, if I sell a commercial system this, the price tag isn't going to be much lower, about $4,500. And my job here is to make a business case that is worthwhile. And if you guys want to experiment, I'll bring you in the project and we can make a deal. But when it comes to putting these things in boxes with the inevitable feature of doneness and workability, it's not going to be a bargain basement thing. And that would make it worthwhile to consider custom actuators with some redundancy, or maybe even dual actuators driving a walking beam that gives you functional redundancy in case one of the two actuators fails, or something like that. Murray, you have a question?
It sounds like there's no interconnection with the trim system, is that correct?
It sounds like there's no interconnection with the trim system. That is correct, and that's an important thing to consider. One of the things that makes the LS6 so nice to fly is that if you move the flap lever, it actually uses a spring to bias the stick to follow the speed that accommodates that flap setting. We don't have that now, but I've been looking into incorporating it by simply, using a spring between that torque tube I showed you and the elevator push-pull tube, and it turns out they're both in pretty close proximity, so it's a very realistic thing to do. But, I have to pick my battles, and then I have to choose those battles carefully, and then I have to put some of those battles back in the box for next time. Next question? Sir.
What kind of performance
Say it again. Performance improvement. That's a good question. We're going to do a bunch of data logging and see what we get. Right now, I think we're looking maybe 2%. But the big thing is making it easier to fly, which doesn't always show up in performance and often shows up more in terms of how we feel about your flight. But if we can show data logging that demonstrates 2% performance improvement, there are people out there who kill for this. Another question?
Yeah.
Yeah.
I noticed while I own this particular glider was going together here outside, that no matter what I did with the flat panel, if I went to positive or negative when we cruise, that the L over D went down. And I don't, to be honest with you, I don't see how.
So whatever you do with the flaps, the L over D goes down.
That's correct. I put negative in, and the electronics would be telling me my L over D, and it would decrease.
Interesting. What type of glider is that?
ASW20, this particular one.
ASW20. Interesting. Yeah, I don't have an answer to that. I mean, the flippant response is, wow, that sounds like a really poor glider design, but I have to know, Gerhard Vandel is not a bad glider designer.
Yeah.
It could be what your instruments are showing you, and it could be that the L over D decrease, it would be worse if you didn't use the flaps. I don't know. It's all about of all the different parameters that go into determining the CL that determines what the proper flap setting would be. That includes, you know, mass, speed, G loading, yeah, those are the big ones.
Would the effect be your positive effect, would it be a very transitory thing? Another just a few seconds and then has to change to some other,
I'm not sure I understand.
well, I say you hit a sharp gust.
Yeah.
Then your flaps are gonna do something to
Yeah.
your system.
Yeah.
And, but once that transitory thing is gone,
Yeah.
then you still will have to.
Yeah, they go back to whatever they were before. You know what? We're gonna have to fly this thing and see what we get out of it. And then I can start making promises.
And I made mine a standard ship by just leaving, when I was in cruise, I just put the flaps in neutral and.
Yeah, and
buckle up.
and you know what? That's not so bad. But it's not so bad. I've done that, but it's not perfect. And the difference between that and putting the flat panel in the proper spot adds up. Remember George Moffat talking about, you know, the difference between first place and fourth place might be a matter of seconds every few minutes. And this is where I'm trying to save you a couple of seconds. Bill, do you have a question?
Just a comment. What he's describing could be the gap seals and flaps.
Oh, so maybe if you had proper gap seals and an internal curtain seal, you wouldn't see the performance loss.
There will be a loss.
Yeah. Yes, Maria.
The function of flaps in most sailplanes is to keep the airfoil in the drag bucket.
Okay.
And the flap sailplane can have lower drag, narrower
Yes.
drag bucket because of the flaps, whereas non-flap ship has to be designed with a wider drag
Oh,
bucket.
interesting. Did y'all get that? Yeah. What Murray's saying is that when you design a flap sailplane, if you do it right, you can make the drag bucket narrower because you know that you can stay in that drag bucket by adjusting the camber.
And what it's adjusting is getting the stagnation point at the optimum point on the leading edge of the airplane.
Moving the stagnation point, the optimum point of the edge
The
there.
flap, if you look at smoke tunnel footage of the effects of trailing edge devices on what happens at the front of the airfoil, it's really dramatic.
Now that's an interesting point. Steve Smith showed me this a while back, and it's really weirdly counterintuitive. As you adjust the flaps, as you adjust the camber at the flap line, the largest effect aren't the pressure distribution around the flap. The largest effects are the pressure distribution about the leading edge, which is weird.
Pretty impressive.
But that's what we're looking at. Any other questions? All right, I think we're done here. Thank you so much.